Okay, before we get into it, a couple announcements. So, as you should know by now, the quiz is on Thursday. It'll be for the first half an hour of class starting Berkeley time, so we'll go from 3:40 to 4:10. If you have DSP accommodations, please reach out to the DeCal email, hopefully by tonight, so that we can arrange something. It'll cover content from lecture 1 until today, but if I recall correctly, lecture 1 might have been the one where we did the things on numerical bases and the polynomial guessing, so you don't need to worry about that. So just starting from when we started talking about sets and functions until now. And this roughly corresponds to chapter 1 in our textbook, okay? No cheat sheets. Someone asked about that on Piazza. I highly recommend you attempt homework 2 before the quiz because all of the material on homework 2 is pertinent to the quiz, even though it's only due on Friday. I also would recommend looking at last semester's midterm. The solutions for that are also on the website. Time permitting, at the end of today, we'll go over one of the questions from there that I thought was relatively challenging. And there's also a walkthrough video for homework 1 that I made over the weekend. I highly recommend you take a look at that as well to make sure you're rock solid on the content from 1.1 and 1.2 in our book, because that will sort of serve as the basis of everything that we do moving forward. And there isn't necessarily a way for me to guarantee that you looked at the homework solution, so maybe the walkthrough video is slightly more digestible. I can't guarantee that I'll be able to put this together for every homework, but it exists for homework 1. You had a question up here?
Yeah, I had like 2 questions. One is that for the midterm, when is that this content of the midterm that you have uploaded?
Yeah.
Is it the same as what's on the quiz?
No. I think I mentioned this earlier, but last semester I taught this with the standard midterm and final format, whereas now we just have 5 quizzes. So the midterm was way later in the semester than this quiz is. So not most, but a lot of the content on the midterm will not necessarily apply for this quiz. So any question that really asks you to prove anything, especially with induction and that sort of thing, you can ignore that. I don't really have a mapping of which questions are relevant and which questions aren't, but you can sort of make that judgment for yourself. Yeah.
For the grade, the homework 1 grade, I looked at grade school, we didn't really get it out of 5.
Yeah, it's not graded yet.
Oh.
Yeah. And either way, the homeworks will be graded on completeness and effort, not correctness. So the way you should be checking to see if your homework, if you did it correctly, is by comparing it with the solutions, which are already up. Okay? The grade is really just to make sure that you did it, but it doesn't really tell you whether or not you did it correctly. So I highly, highly recommend you either watch the homework walkthrough video or check your homework versus the solutions to make sure you sort of did this correctly. There's another question? Are they cumulative? Not necessarily, so for this one it doesn't really matter, but in the future it will be primarily focused on the material between the last quiz and the current quiz, but some of that material may rely on material that was earlier in the course. So in that way, it's not cumulative, but for a lot of the things later in the course, you'll need to know things we did now. Okay? Any other questions? Also, a couple of you noted a couple typos in the textbook. That's great. Please let me know if you ever find anything that just looks wrong in the textbook, because if I was up at 3 a.m. writing something, there's a good chance it could be wrong. So if you find that, let me know. Yeah, question? No? Any other questions? Cool. Also, the add drop deadline is tomorrow, so make sure you've enrolled in the units for the course by tomorrow. Okay, because otherwise you won't be able to. I think most people have. Okay, so let's get into it. So last week we left off talking about propositions and logical operators. So a proposition, we said, is a statement that has a definitive value, so it's either true or false, okay? And this is in contrast to an opinion, which differs based off, depending on who you ask, right? There's no definitive value of an opinion. Whereas a proposition has a truth value, okay? And the way I like to look at more complex propositions are as functions where the variables are just true or false, okay? And we looked at 3 logical operators that allow us to form more complex propositions, and we'll see this a lot when we get to proof techniques. And these will form the basis of everything we'll see in propositional logic. So we saw the conjunction, which was the same as and, the disjunction, which is the same as or, and the negation, right? So the first one we saw was the conjunction that reads A and B, which is true only when both A and B are true, okay? And we said that this is very similar to the intersection in set theory, right? The intersection of A and B is a set of all elements that are in A and in B, okay? And this truth table is what the structure is called, gives us the definition of the A and B operation. So on all possible combinations of inputs, it tells us what the outputs are. Okay? And since A only has two possible values, true and false, and B only has two possible values, true and false, there are 4 combinations of inputs to A and B. So any questions with the conjunction? Okay? Then we also looked at the disjunction, A or B, which is true when either A or B are true, right? And this is not an exclusive or. It's true when at least one is true, but it's also true when both are true, okay? And so the way you can think about this is in terms of the union. Okay, the union includes everything that's in A as well as everything that's in B, okay? And so A or B is true when both are true, when only one is true. It's just false when neither of them are true. Is that clear? So this is a truth table defining the operation for A or B. Any questions with this? Okay. And lastly, we looked at the negation, which reads not A, which essentially just flips the value of A. So not A is true when A is false, and not A is false when A is true. And so, this should read the complement of A. The complement of A is a set of all elements that are not in A. Right? And that's the parallel between set theory and propositional logic. And that's a truth table defining the negation operation. Right? And so suppose we have 3 propositions, U, which tells us which is true when x is under 30, P, which is true when x is prime, and E, which is true when x is even. Then this structure I've written here reads x is under 30 and not prime or even. Okay? So we replace all of these with ands, all of these with ors, and all of these with nots, and sort of read it from left to right. There's a question in the back.
In the special notation, could you also just not, instead of using the not symbol, do you just write a slash through the E?
Yeah, you could also write this as x such that x is not in A. Yeah, that works. Yeah.
Where does the Q come from?
Where's there a Q? Oh, I see. Okay, yeah. Sorry about that. Yeah.
And it says either, but it still means like both, right?
Yeah. The reason I wrote either is to differentiate it, because a lot of times when you hear or in regular English, you'll think it's one or the other, but not both, right? And so that's an important distinction you need to make. Our or allows both to be true, okay? Unlike conversational English. Is that okay? So the regular or operation, yeah, you know what? Why don't we get rid of either there? Because that might incite some confusion. Okay, so x is under 30 and not prime or even. Okay? And you just need to remember the difference between our or and the conversational English or. Okay? So now we can revisit what we defined as being De Morgan's laws in set theory. Remember, De Morgan's laws in set theory allowed us to rewrite an intersection of a complement as a complement of intersections, and the intersection of, the union of complements. Sorry, I said that the wrong way. It allows us to write the complement of an intersection as the union of two complements, which is what the first does. And it allows us to write the complement of a union as the intersection of two complements, which is what the second line does. All right, so notice, if we take the complement of A intersect B, we complement the individual sets and change the intersection to a union. And this is something we've already seen in set theory, right? Remember in lecture we calculated the example where A and B are both sets containing numbers between 1 and 10, and we calculated the intersection of A and B, took its complement, and then founded A complement and B complement individually and took the union, and they happen to be the same thing. Yeah.
Does this work for like more than two sets?
It does. Okay? And so that was for sets, but now we're talking about propositional logic. And it turns out that the same rules apply for propositions P and Q. Well, I could have used A and B, but just to differentiate it, I used P and Q. So the negation of P and Q is not P or not Q. Right? Notice how these are essentially saying the exact same thing, right? And the negation of P or Q is not P and not Q. Okay, so notice these are really saying the same thing, just with our set theory symbols changed to propositional logic symbols. Okay, and they're both referred to as De Morgan's laws. Yeah?
What's the difference between like the upper equals to and the lower equals
Yes. Great question. So in propositional logic, we talk about statements being equivalent. Okay? Whereas on the top, we're talking about two sets and saying that they're the exact same set. Okay, so we say that these two are equal. In propositional logic, this triple equal sign means equivalent. Okay? And so what I'm claiming to you right now is that the negation of P and Q is logically equivalent to not P or not Q, which is this first line. I'm saying that the left-hand side and right-hand side are logically equivalent. So, in other words, what I'm saying is, on all combination of inputs, these two expressions return the same outputs. Okay? And so we're about to show how you can prove such a statement. Okay, so any questions with the basic premise of these De Morgan laws? So we go through, change conjunctions to disjunctions and vice versa, and then negate individual propositions. Okay? So again, the structure we use to prove two logical expressions to be equivalent is the truth table. Okay, and I believe this is a question on homework 2, right? And so what we've done here is my claim is that not P and Q is equivalent to not P or not Q. And what I've done is on all possible combinations of inputs, so true, 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 false, false, true, and false, false, I've evaluated the value of this expression, both expressions, right? And at first I do not P and Q, and we know P and Q is only true when both P is true and Q is true. And so it's the opposite since we're taking the not of it, right? If we're just looking at P and Q, this would be true, false, 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 right? Because the way we've defined P and Q is that it's only true when both are true. Since we're taking the negation of it, we flip them all over here. Is that okay? And then the next, the one I wanted to compare it to was not P or not Q. And so what I'm doing is saying if P is true and Q is true, what's the value of not P or not Q? Well, if P is true, not P is false. And if Q is true, not Q is also false. And false or false is still false. So that works. And then in all of the other ones, at least one of not P or not Q ends up being true. And if at least one of the elements in an OR is true, it evaluates the true. Okay? Just to clear it up a little, what I've done is this. And so what I've shown now is that on all combinations of inputs, the left-hand side of this expression and the right-hand side of this expression evaluate to the same thing. So therefore, we can say not P and Q is logically equivalent to not P or not Q. Is that clear? I've tested it on all possible inputs, and they return the same thing. It's as if, like one way you could think about it is if you, think back to trig in high school and you did some sort of trig identity thing, right? And if you, not that this is the same thing, because what we've done here is shown it's true on all inputs, But if you had a trig identity and you simplify it to something else, and you test it on like 10 inputs and they give the same thing, your guess is that they're probably the same thing, right? Whereas there, I mean, you technically have to try it on all real numbers to do the similar thing, which you can't. But here, we've shown that on all possible inputs, these two functions, if you want to think of it like that, are equivalent. So they're equivalent. Is that okay? And so we could also do this for the other version of De Morgan's laws, right? So I could say P, Q, not P or Q, and not P and not Q. Okay, so I could do, let's see, true, 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 false, false, true, and false, false. Okay. Not P or Q. We know that this, the thing inside, or the thing that I'm highlighting right now, if at least one of our variables is true, this will evaluate to true. But then we're flipping it because we're taking the negation. So this will be false, this will be false, and this will be false. Lastly, if we have false or false, that will be false. But we're taking the negation of that, so this will be true. Okay? And what you can do is do a similar thing, show that on all combinations of inputs, not P and not Q have the same outputs as the third column. Right here, this ends up being false and false. This ends up being false and true. False and true, true and false, and this is true and true, which is true. Okay? So what we're showing is that on all combinations of inputs, these two things give the same results, therefore they're logically equivalent. So in general, if you're ever asked to show that two expressions are logically equivalent, like, for example, on a quiz, what you would have to do is draw a truth table and show that on all combinations of inputs, they return the same outputs. Any questions with the idea of a truth table? Yeah?
What about a P implies Q? What would the truth table?
We're getting there. We're getting there. Cool. So I'll give you an example to try out really quick amongst yourselves. Find the negation of the statement T is even and not prime or irrational. T is even and not prime or irrational and prime. Okay? You can draw the brackets here if you want. So T is even and not prime or irrational and prime. What is the negation of that statement? Okay, and so what I'll do is I'll just assign variables to mean each of these things. Okay, so I'll say E is the proposition T is even, P is the proposition T is prime, and I is the proposition T is irrational. Notice these are all propositions. Given some value of T, each of these is either definitively true or definitively false. Right? And so let's write this. Our first statement says T is even, that should be an E, even and not prime, or irrational and prime. Is that clear? So this is our original statement. And so now what I want to do is take the negation of this. So what I'll end up doing is propagating this negation symbol along the expression. So negation will be the negation of this entire thing.
So negation is just the same as saying not this.
Not, exactly. So I could say it's not the case that this entire expression, but that's a little lazy. So what we'll do is propagate this negation sign throughout the entire expression. And so the first rule we'll use is the fact that not A or B is equivalent to not A and not B. And so in this case, you could think of this as being our A and this as being our B, right? Because it's just two things separated by a disjunction. Okay? So what I'll say is that this is equivalent to not E and not P, or not I and P. So we're sort of working from the outside in. Now I have to redistribute the negations within the individual parentheses. You had a question? Yes. No. I do mean it. You're right. Good catch. Okay, because when it's really just an application of this rule. When you take the negation of an or, it turns into the and of two separate negations. Okay, so here I've applied the first law, and then now what I'll do is distribute the negation within the individual parentheses. So here I'll have not E or not P. Why is it double not? Because there's already one not to begin with. Okay? And so here I'm using the rule not A and B gives not A or not B. And that's the rule I've used over here. The and will stay, and then I'll have not I or not P. So move this up a little. Okay, and our last simplifying step can be not E or, well, what's a double negative? We can just sort of cancel that out. So we have not even or prime and not irrational or not prime. So if we wanted, I could now translate this back to English and say the negation of the original statement is T is not even or prime and not irrational or not prime. Okay, so this is how you would find the negation of some statement in English. We'd, convert it to propositional logic first, use De Morgan's laws, rewrite it using the two rules that we have, and then and convert it back into English. So any questions with this? Yeah?
On the second step, after you distribute the not, do you need the parentheses after that? Or is that just like a format?
Where is this?
On the second step of the loop, the negation.
Like here?
Yeah. Once we distribute the nots to each side. Like, do we need the
You're seeing this.
Yeah. Do we
Just to keep it clear, I think it would be good to keep it. Yeah. Yeah. The process of flipping things?
Yeah, or how come we didn't end on the step above or something?
Well, just because here we had a double negative, and that looks a little odd. You sort of have to propagate it through your entire expression. Yeah.
If you didn't give us the parentheses in the words, is there a general way to do it, or do you have to give us the parentheses?
So this is sort of just a question I made up, but in other cases it'll be clear what the distribution of the ands and ors are, because that does change things. Yeah.
So is this the most it can be simplified, or can it be simplified?
Knowing nothing else about the propositions and just treating them as just letters at this point, no, you can't simplify this any further. Yeah.
We got at the end of the negation, I noticed it was just everything in the original but flip. Is it always going to be that case? Because E just becomes not E, and the and just becomes more.
Yeah. That's the whole point. That's the. I guess that's the beauty of De Morgan's laws. You end up flipping everything. The P's become not P's, the ands become ors, Q's become not Q's. You flip everything. Yeah.
Is there an order of operations for the and or?
Not for our purposes. For our purposes, we can stick with just parentheses saying this is one group and with this is another group. You probably don't have to worry about that for our purposes. Yeah.
But on the third step, what does it change in the
So you're saying this line?
Yeah, why didn't we change the and?
Because we're distributing this negation into this parenthesis.
So it changes the operation.
It all, yeah, because that's what De Morgan's law says right here. It changes the operation as well as the individual pieces. Good, I like the questions, but I want to move on because there's a lot of material to cover. Okay? So another operation that we can study that's a composition of the negation, conjunction, and disjunction is the exclusive OR. Okay, so our regular OR operation is true when both are true and when only one is true. It's really only false when neither is true. Okay? So we have this exclusive OR, A, X, or B, which is true when exactly one of A or B is true. Okay? So notice here, it's false when they're both true. Okay? And so this is only true when exactly one of them is true. So any questions with how A, X, or B is defined? Okay, so now my question for you is, can you rewrite A, X, or B in terms of our standard or, and not operations? Okay? And so the task is, try and come up with some expression that evaluates to exactly this on the corresponding inputs. So I'll give you a minute or two to attempt that and see if you can come up with an expression. And there's not one correct answer necessarily.
How old is this type of addition?
For exclusive OR,
Yeah.
I'm not entirely sure why.
Zodiac.
Pardon? Zodiac? Why, have you seen something else?
No, just like it's kind of random, like how weird the notation is. That represents XOR.
Yeah, I'm sure it has some like similarities with like bit operations and that sort of thing. And in different places they'll be defined differently. Oftentimes you'll just see A, X, or B like written out. Because I mean like the or, and not, like those are pretty standard. Even not, sometimes you'll see as like not. But for these kinds of things it tends to vary. Okay, let's come back together. Can someone give me an expression that they found that is equivalent to A, X, or B? Yeah.
I got in parentheses A or B,
Okay.
and then negation in parentheses A and B.
Okay. So how did you get that?
Well, I know that like in every other case, the inclusive or is just the same as the regular or.
Yeah.
Except in the case that when they're the same, so we can just say explicitly that they can't be the same by just using the negation of these.
Exactly. That's exactly right. So what we're saying is we notice that in the last three cases, exclusive or and regular or are the exact same, right? True, true, false, true, true, false. So we can start with A or B. What we want to change is the behavior on the inputs when both are true. Okay? When both are true, we want it to be false. So what we can say is, and it's not true when A and B are both true. This is just a direct translation of how we could think about it. Okay? And so if we wanted to go and prove that this is the case, we could do so with the truth table. Okay? Evaluate it on true, 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 false, false, true, and false, false. This is essentially how we've defined it. And what we go do is here, apply, or insert our combinations of A and B into this expression and look at the output. And we find that they're both logically equivalent. And I mentioned before, there isn't necessarily only one correct answer. Why is that? Well, I could have used De Morgan's laws to simplify the second parentheses, right? I could have said A or B and not A or not B, right? And that's equivalent using De Morgan's laws. Is that clear? So again, an exercise that you'll have to do both later today and beginning of class on Thursday probably is, given some expression that we arbitrarily create, come up with some combinations of conjunctions, disjunctions, and negations that happen to be equivalent to this thing we've defined. Is that clear? Okay, and we can always do this because you can think of negations, conjunctions, and disjunctions as our like basis for all expressions. Okay? And another interesting problem you can look at is, okay, here I've created this new operation. Is this also a basis for all other propositional statements? Right? It's like you come up with two arbitrary vectors in R2. Is this a basis or not? Can it be used to create everything else? And that's something we'll look at the end of today. So any questions with this? So truth tables you have to be familiar with. Okay. So now we'll get to implications, which we've indirectly talked about in previous lectures. So this, P implies Q, says that if P is true, then Q must be true. Okay? So that's the most important part. If P is true, then Q must be true. If P is false, however, it doesn't say anything about Q. Q could be either true or false. The implication still holds. Okay? So for example, if we know that today is December, then we also know that, if we know that today is Christmas, that implies that the current month is December. But if we don't know that it's Christmas, then the month could be anything. It may or may not be December. Is that clear? So here, we're treating P as today being Christmas, and Q as the current month being December. So if today is Christmas, so if P is true, then Q has to be true. Okay? So it's impossible for it to be Christmas and the month not to be December, unless you're looking at like Orthodox Christmas or something. If today is not Christmas, then the month could be anything. Is that clear? So this is the truth table, again, that defines an implication. And you will have to know this by heart, because we will use it extensively when we talk about proof techniques. Okay, so this truth table, probably the most important one that you'll see in this class, probably even in future classes. Yeah?
Why does false equal true?
Because the whole premise of an implication is that it only, like the condition is only when the first part is true. If the first part is false, it doesn't say anything about the second part. So the implication is allowed. Okay? And so a better example of this is thinking of an implication as holding a promise. Okay? So suppose I make the promise to you, if it rains tomorrow, I'll give you $100. Okay? The truth value of the implication is just whether or not I hold my promise. Okay? So if it rains tomorrow and I give you $100, did I hold my promise? Yes. Okay? If it rains tomorrow and I don't give you $100, that's the only case in which I broke my promise. So in that case, the truth value is false. But if it doesn't rain tomorrow, no matter what, I kept my promise, because the initial condition was not true. So whether or not I give you $100, if it doesn't rain, I still kept my promise. Is that clear? So you can think of an implication as whether or not you hold a promise. Okay, and the only time you break the promise is when the condition is true and then you don't follow up with it. Okay? It's important to realize implications are just expressions with a truth value. So an implication is no different than, P implies Q is no different than P XOR Q, or not P and not Q. It's the exact same sort of thing. Okay? Any questions with the truth values of an implication? Yeah,
Can you go back a slide just for a second?
sure.
Thank you.
Okay, so the new question is, can we rewrite P implies Q in terms of the conjunction, disjunction, and negation? That's our new problem. Okay, we want to rewrite P implies Q in terms of the three main logical operations we've seen. Okay, so I'll give you a minute or so to try and figure it out, and then we'll come back together. This one? Yeah.
Can you explain again why implications are expressions versus sounds?
It'll be a little more clear once we find out the equivalent way of writing P implies Q in terms of the things we've seen before. Okay? But at a more higher level, like this is just an input, this is just an input, and this is just an output. Okay? So P implies Q is the same as P or Q or P and Q in that it just takes in inputs and returns an output. Is that okay? Okay, any ideas? How can we rewrite P implies Q in terms of our standard three operations? In the back.
Not P, union Q.
So not P or Q is our guess. Any other guesses? Yeah. So you're saying P and Q or not Q? Yeah.
So just be P and true. Now, because if the case false, then it can be false.
Yeah, but so the reason this doesn't work is in the false case, this would be false, but it's supposed to be true.
But Q is
It has to work on all combinations of inputs. Yeah. Do you have one?
Parentheses P and Q
Or not P? Okay. So I like that we all came up with expressions. The standard form that we'll see is actually this one. I haven't thought about whether your expression evaluates to be correct or not, but if you did the truth table and it ends up being correct, then it's a valid expression. Okay? So the standard way we'll write, one second. The standard way we'll write P implies Q is not P or Q. Okay? And hopefully this illustrates why the implication is just another logical expression with the truth value, right? Because we've written it in terms of negations, conjunctions, and disjunctions. Okay? It's the exact same thing as this expression, not P or Q. Yeah.
Is there a way to write it with XOR?
I'm sure that like you could figure it out, yeah. Yeah. And that's the thing. Like we could define any operation we want and try and rewrite anything else in terms of it. And that's something we'll do at the end of today. But for our main purposes, we'll stick with writing it as not P or Q. Okay? So it's just another logical expression written in terms of ors, ands, and nots. Okay? And so this is an equivalence that we will see very, very often when we do proofs. Okay? Okay, just as an illustration, if we have x is even implies x squared is even, this is logically equivalent to x is odd or x squared is even. Okay, but this is P, this is Q, this is not P, this is our OR, and this is our Q. And you can always think about the truth table if this ever seems a little odd. Okay? So now, a question is, how do we find the negation of an implication? Okay? So, consider the following statement. If t squared is prime, then t is not an integer. What's the negation of this statement? I'll let you think about it. And you might want to try and use De Morgan's laws. Like first, you might want to just abstract the whole t squared and t thing away to this being p and this being q. And use De Morgan's laws to try and find the negation of the implication. Pardon? Yeah, this is an implication. This is indeed an implication. It's of the form if P, then Q. Right? And we sort of said that before. I guess I didn't explicitly write this, but implications are always of the form if P, then Q. Okay? Was that clear? Implications are if P, then Q. Okay? Any ideas on the negation of this statement? Why don't we go back here? Yeah. Okay, so it's not, the negation of this doesn't come in the form of an implication. Did you have an idea? Exactly. Okay, so let's take a look at this. We know that P implies Q is the same as not P or Q. What we want to do is find the negation of this. So the negation of P implies Q is the same as the negation of this thing, not P or Q. Is that clear? And when we take the negation of an or, we switch it to an and take the negation of the individual pieces. So we'll say this is not P and not Q. Right? Which the double knots go away and we have P and not Q. So in terms of this statement, the negation would be t squared is prime and t is an integer. Okay, notice yet we haven't concerned ourselves with figuring out whether or not these propositions are true. These are just examples that I've come up with. The task of determining whether or not these propositions are true is what we'll do when we start studying proofs, probably on Thursday. Okay, for now we just need to know how to manipulate these things, take the negation of these things, and be familiar with this notation. Okay? So the negation of the statement, if t squared is prime, then t is not an integer, is t squared is prime, and t is an integer. Okay, so this is P and not Q. Is that cool? And this result is very, very important. Okay, P and not Q. This is a form that you need to know. Okay, the negation of an implication. Any questions with this? Okay, cool. So now we'll look at two extensions of the implication, the contrapositive and the converse. Okay, and these are both implications themselves, and they share, some things in common with the original implication. Okay? So the first one we want to look at is what's called the contrapositive. Okay, so if our standard implication is P implies Q, its contrapositive is not P implies not Q. Okay? And so if a statement says if P, then Q, the contrapositive says if not Q, then not P. Okay? And what we have here is an example of us using De Morgan's laws. Actually, we don't even use De Morgan's laws here. We just use the fact that an implication of the form A implies B is equivalent to not A or B. We use that going from this line to this equation to this equation. Expression, I should say. And rearranged. And so this shows us that not Q implies not P is the same as P implies Q. Okay, and so what really helps illustrate this is looking at examples in English. So for example, if the statement is, if it is sunny outside, I will wear my sunglasses. The contrapositive is, if I don't wear my sunglasses, or if I'm not wearing my sunglasses, it's not sunny outside. Because whenever it is sunny, I'll wear my sunglasses. So if I'm not wearing my sunglasses, it's not sunny. Is that clear? Those two sentences say the same thing. Another one, if it is a square, it is a rectangle. Right? That's equivalent to saying, if it's not a rectangle, it's not a square. Because all squares have to be rectangles. Is this clear? So a statement and its contrapositive mean the exact same thing. And we've shown that right here. And another thing you could do is go through, draw the truth table, P, Q, P implies Q, not Q implies not P, and do that and show that these two columns will be the exact same. And that would be another way of showing that the contrapositive is equivalent to the original implication. I just did it here with the fact that A implies B is the same as not A or B. Okay? So is everyone okay with the idea of a contrapositive being equivalent to the original statement? And the contrapositive of if P then Q is if not Q then not P. Sounds good? Okay. The other extension of the implication we want to look at is the converse. Okay? And oftentimes when first learning this, people confuse these terms. Converse, contrapositive, because I guess they both start with con, and they're related to implications. But they're very, very different things. Okay? So the converse of P implies Q is Q implies P. But this is not equivalent to the original statement itself. Okay? If a statement reads, if P then Q, its converse reads, if Q then P. Okay? And the converse is not necessarily, and in most cases isn't, equivalent to the original statement. In some cases, you'll see, though, the converse and the original statement are equal, they're equivalent, and there's a special case for that. Okay? So, as an example, if it's sunny outside, I'll wear my sunglasses. Its converse is, if I wear my sunglasses, it is sunny outside. But what if I always wear my sunglasses? Right? It doesn't, just because I'm wearing my sunglasses doesn't mean it's sunny. All I'm saying is, if it is sunny, I'll wear my sunglasses. But I could also wear my sunglasses if it's cloudy. And the converse is definitely not true. Okay? Another more obvious example, if our implication is, if it is a square, it is a rectangle, its converse would be, if it is a rectangle, it is a square. But that's also not true, because not all rectangles are squares. I'll skip the third one for a second. Let's look at the last one. If today is Christmas, it's currently December. That's a valid implication. But if it is currently December, it doesn't tell you that today is Christmas. So that is the converse. If it is currently December, then today is Christmas. But we see that these two sentences don't mean the same thing. Okay? And so the third one, if F is a bijection, it is both an injection and a surjection. The converse of that statement is, if F is both an injection and a surjection, it is a bijection. And so in the third case, both expressions happen to be true. Right? And so this is a special case. Both are true. So is everyone okay with how to, given some sentence or some statement, how to write its contrapositive and how to write its converse? Let's get some practice with that. Okay? So suppose our statement is, if P and Q are prime, then you could put the parentheses around here, I guess. But then, the greatest common divisor of P and Q is 1, or P is equal to Q. Okay? Don't worry about the whole greatest common divisor thing, or like the actual validity of the statement, right? Because we haven't talked about whether or not things like this are true, or proving things. This is just a statement that I came up with. Determine the contrapositive of this, and the converse of this. Okay? And remember, if our implication is P implies Q, the converse is Q implies P. Oops. And the contrapositive is not Q implies not P. Okay? And I assume if this is our P and this is our Q, you'll have to take the negation of the Q, which means you'll have to use De Morgan's laws because there's an or in there. So try and determine the contrapositive and converse of these statements. Okay, and before I take it up, there is an example of the contrapositive that we talked about maybe a week ago. Okay? When we talked about the definition of an injection, I said that there's two ways that we could refer to this. Right? One way was if f of x1 is equal to f of x2, that implies that x1 is equal to x2. But the other way I phrased this was if x1 is not equal to x2, then f of x1 is not equal to f of x2. Does this sound familiar? Right? When we talked about the definition of an injection, I just said that those two things are equivalent, but now we know why they're equivalent, because the latter is the converse of the former. Okay? To make explicit, this is P and Q, this is not Q, this is not P. Is that clear? Definition of an injection. Okay? So what's the contrapositive of the statement that we're given? Actually, let's do the converse first, because it's a little easier. What's the converse of this statement? Any ideas? Converse of the statement. Yeah.
If the GCD of P and Q is 1, or P equals Q, then P and Q are prime.
Great. What's the contrapositive? Yeah.
If the greatest common denominator of P and Q does not equal 1, and P does not equal Q, then P is not prime, or Q is not prime.
Great. So the contrapositive says if the GCD of P and Q is not 1 and P is not equal to Q, then at least one of them is not prime. Okay, and notice the negation of both are prime is at least one of them is not prime. Right, which is the same as it's not the case that both are prime. If it's not the case that they're both prime, at least one of them is not prime. The converse is really just switching the thens and ifs, right? The converse is if the GCD is 1 or P is equal to Q, then P and Q are prime. Okay? Theoretically, at least for the purposes of what we know now in this class, they could both be true. I mean, the contrapositive is true if the original one is true. The converse could be true. It happens to not be the case, right? Because, for example, 5 and 12 the GCD is equal to 1, but they're not both prime. But that doesn't matter for now. Determining the validity of these statements is something we'll start doing on Thursday. But all you need to know for now is how to find the contrapositive and how to find the converse. And I believe there's practice with that on the homework. And I can guarantee you, essentially this exact same question with a different statement will be on your quiz on Thursday. So make sure you're able to do this. Is that clear? Cool. And so another extension of the implication is this idea of if and only if. And it's something we saw a little bit when talking about, bijections, injections, and surjections. Something we said was, a function is bijective if and only if, which is this if with two F's, if and only if. It is both surjective and injective. So if and only if, A if and only if B, rather, says that A is true only when B is true, and A is false only when B is false. Okay? So really what this is saying is that A and B are the same proposition, the same statement, right? And we see that. The statement, a function is a bijection, is the exact same statement as a function is both surjective and injective. They mean the exact same thing. One implies the other and vice versa. Okay? And so another way of thinking about this is A if and only if B is true when both an implication and the converse are both true. Right? So going back to this example here, in the third example, since the converse of the original statement is true, we have that the statement is an if and only if. But in the other cases, it's not the case. So for example, I couldn't say a shape is a square if and only if it's a rectangle. That's not true. It's a rectangle if it's a square, but it's not a square just because it's a rectangle. Okay? And so another example in terms of, colloquial things we talk about, it is Christmas if and only if it is December 25th, decomposes into two separate implications. Right? Every time you have an if and only if, that's really A implies B and B implies A. Okay? This tells us one, that it is Christmas if it is December 25th. And the other is that it is December 25th if it is Christmas. Okay, I sort of wrote these in the opposite way that you normally look at it. This one, the if is coming after, but so if it is Des 25, then it is Christmas. If it is Christmas, then it is Des 25. Okay? And essentially what all this boils down to is that these two statements are equivalent. Okay? The fact that it's Christmas and the fact that it's December 25th mean the exact same thing. Yeah?
So this would just be like A equals B then?
A is equivalent to B, yeah. Cool. And what we're really showing when two statements are equivalent is that one implies the other and the other implies it.
Is this?
Okay. And here's a truth table illustrating why this is the case. Okay. So here we have A implies B, which is true when both A and B are the same. So it's true when we have true, true. And it's true when we have false, false. And if you work out the truth table for A implies B intersector and B implies A, you get the same thing. So you could say A implies B is equivalent to A if and only if B is equivalent to A implies B and B implies A. B implies A. Is that okay? Cool. And so it's an understanding of if and only if, and the fact that it's really just two separate implications is very important for proof techniques. Okay? So when we end up proving something if and only if something else, you actually have to prove both directions, that one implies the other and vice versa. Okay, and now that we formally know what an if and only if implication is, we can use this going into when we start proving things. Is that okay? Any questions with this idea of if and only if? Cool. I think we'll actually finish today. Next, we'll talk about existential and universal quantifiers, which we actually have seen before when talking about the definition of a surjection. Okay? So we have two. We have the universal quantifier, which is the upside down A that we've seen, which means for all. And we also have the existential quantifier, the backwards E, which reads there exists. Okay, so we have for all and there exists. And so remember, we said that a function mapping from domain A to codomain B is surjective. We can even replace this with an if and only if, now that we know what that is. For all B in the domain, there exists some A, for all B in the codomain, there exists some A in the domain, such that B is mapped to by f of A. Right? We've seen this before. For all and there exists. But now we're formalizing this. Okay? So for example, suppose E of x is the proposition x is even, and U of x is the proposition x is odd. What do the following statements mean? Can someone tell me what the first one means? What does the first statement mean? Yeah.
For all x in natural numbers, x is even or it's odd.
Exactly. This first one says, for all natural numbers x, or for all x in the natural numbers, for all naturals x, x is even or x is odd. Great. That happens to be true. Okay, again, we don't really want to think about what these statements mean, or like whether or not they're true yet, but just to, define things. What does the second one mean? It's almost the same thing, with just the or replaced with an and, right? So this is saying for all natural numbers x, x is even and x is odd. It's not true, but that's what it says, right? All naturals x, x is even and x is odd. This is true, this is false, but that's besides the point. Okay? So now we formally looked at existential and universal quantifiers. So the last thing we sort of need to wrap all of this up is De Morgan's laws for these quantifiers. Okay? And so De Morgan's laws actually allow us to change a universal quantifier into an existential one and vice versa. Okay? So for example, the negation of for all x, P of x is true, or P of x is just some proposition, is there exists some x that P of x is not true. And the second one says if it's not the case that there exists some x that P of x is true, then for all x, P of x is not true. Okay? So for example, why don't we let x represent the set of students in this class, and P of x be the proposition that a student is a sophomore. Okay? So what does the first one say? It says, if not all students are sophomores, then there exists at least one student that is not a sophomore. Is that clear? So, not all students are sophomores. So, and this says exists a student okay, so if not all of our students are sophomores, then there exists at least one person that's not a sophomore. Right? Because if there didn't exist one person that's not a sophomore, then everyone would be sophomores. Right? The second one says if there doesn't exist a sophomore, then all students are not sophomores. Is that clear? So what this one is saying, if does not exist a sophomore, this one says all students are not sophomores. Okay, another way of thinking about the last one is no student is a sophomore. No student okay? Okay, so essentially what De Morgan's laws with quantifiers tell us, if not all students are sophomores, then there exists at least one person who's not a sophomore. And if there doesn't exist a sophomore, then really nobody's a sophomore. And both things are saying the exact same thing. So this will allow us to now take the negations of longer statements, but ones that include for alls and there exists. Yeah, in the back.
You're like ranking the first one.
Yeah.
You need a comma after if you're saying for all x, e of x.
So you're saying, do we need a comma here?
Yeah.
You don't need it.
So is that saying for x, for all x, p of x is true?
Yeah.
Okay.
So yeah, another way of thinking about this is for all x, just what's in the box, p of x is true. Is that okay? Yeah.
And then the second one is there exists an x such that.
Yeah.
Okay.
If it's not, yeah. And with the negation, it says, if it's not the case that there exists an x such that p of x is true, then for all x, not p of x. Okay, so what's in the box says for all x, p of x is true. I'll erase that just to avoid confusion, but I guess I can write it down here. What we say by for all x, p of x, for all x, p of x is true. Oops, maybe I can put this over here. Cool. So any questions with the rules? And there's another example on here about p of x being a prime. And so for example, the first rule says if it's not the case, and a lot of times when you convert propositional statements to English, and it's kind of awkward to put a not in there somewhere, you'll just say if it's not the case that the original sentence, right? So if it's not the case that x is prime for all natural numbers x, then there exists some natural number x that's not prime. That's what the first one is saying. It's saying that those two things are equivalent. The second one is saying if it's not true that there exists a natural number x that's prime, then all x that are natural numbers are not prime. Okay? And really, I shouldn't be writing it as if and then, because that makes it seem like it's implication. What I should be writing is these two things are equivalent. So let's ignore the if it. So ignoring what's under the red, the two parts of each of these sentences are the same. Is that okay? And so this is an application of De Morgan's law. So now we have De Morgan's laws for sets. We have De Morgan's laws for our standard conjunction, disjunction, and negation. We also have it for all and there exists. Is that clear? Okay. So now we can find negations of complicated statements, right? And it's not really just for fun. It's because you'll have to do it when we do proofs, okay? So for example, the statement that I have written, the first one, says for all, this should say rational numbers. Okay, and this should be the fancy Q, but whatever. What this is saying is for all rational numbers Q, there exists some T that's also irrational such that Q times T is equal to 1. or q is equal to 0. Essentially what this is saying, and you'll get more practice with converting these things from like a robotic sounding thing with the ors and ands to something that reads a little more smoothly, like all rational numbers q have an inverse or are equal to 0. That's really what this is saying. Right? What the q times t is equal to 1 is saying that for if q is a rational number, there's some other rational number t such that q times t is 1. The t is the inverse, right? The negation of this, well, how do we calculate the negation? We change the for all to there exists. So notice the for all becomes the there exists. This there exists becomes a for all. And the equal becomes a not equal. The or becomes an and the equal becomes a not equal. Right? All right, take the negation. We have the for all becomes there exists. Oops. There exists becomes for all. You can really just say it goes both ways. And the and goes to an or. Is that clear? So we change all for alls to there exists, all there exists to for alls, all the ors to ands, and all the ands to ors. And the equals, I guess, go to not equals. Okay? So now the negation of this, it makes a little more sense when I read it in normal English. There exists some non-zero rational number that doesn't have an inverse. Right? The negation is saying there exists some q in the set of rationals such that for all other rational numbers t, q times t is not 1, and q is non-zero. So what the negation is saying is that there's some non-zero rational number that doesn't have an inverse. And that's the negation of our original statement. Okay? And we can even propagate our negation through a long chain of propositions and quantifiers. So for example, if you want to take the negation of whatever is highlighted here, for all x there exists some y such that p of xy or q of y, the negation of that, really you just have to remember the rules. The for all maps to there exists, the there exists maps to for all, we add a negation to the individual statements and change the or to an and. Those rules will always hold. So there isn't any guesswork that you need to do. Is that clear? Cool. And one more quick note. You can't arbitrarily reverse the order of for alls and there exists. Okay? So for example, suppose p of xy is the proposition that x is greater than y. Okay, so it's true if x is greater than y, not true if that's not the case. So the first sentence that I've written, for all integers x, there exists some y such that p of xy, what that says is, for all integers x, there's some integer y that's smaller than x. Well, that's true because there's no smallest integer. Right? If I pick my x, I can always find some other integer that's smaller than it. Does that sort of make sense? Give me any integer, I can find one that's smaller. However, if I rearrange this and move the there exists part to the front and the for all part second, what I'm now saying is there exists some magical y that's an integer, such that for any integer x, y is smaller than x. So what this is saying is there's some magical y that's smaller than any other integer. But that's just not true, because there's no smallest integer. Right? So these two propositions are saying very different things. So you can't reverse the order of these quantifiers. Is that clear? Is everyone okay with what the first statement says versus what the second statement says? The first says, for any natural number, for any integer, I can always find one that's smaller. The second one says that there is a smallest integer, which is just not true. Any questions with this? So you cannot arbitrarily reverse the order of these symbols. Sounds good? Okay. I'll put up the attendance link, and then we'll work through as much of this problem as we can. Just to remind you once again that the quiz is on Thursday. Okay, I'll allow you to fill that out as we work through this problem because I want to do as much of it as we can in the 4 minutes that we have, I guess.
Oh, no, not for.
No, I couldn't think of one. That wasn't already used. Don't worry, we'll have some after this and on Thursday, especially after the All-Star weekend. Okay. So as I was mentioning earlier, a problem that we like to work on is showing that we can create some new logical operation that's complete, right? And by it being complete, we mean we want to be able to recreate the or, and not operations using our new operation. Okay? And if you look at the last question on the midterm from last semester, it's the exact same as this. And so we want to consider the operation NOR. So A down arrow B, which is true only when both A and B are false. Okay? So the way I'm defining it is that on all inputs other than false, false, this expression is equivalent to false. But when I pass in false and false, I get true. Okay? So that's how I'm defining my new operation. Is that clear? I'm creating NOR, and I'm saying this is the definition for it. And really, to define anything, you need a truth table. So the first question is, can you rewrite A down arrow B in terms of or, and not? So that's the first question. Okay? I'll move through it a little quickly because I want to get through as much as we can. But notice, this truth table is the reverse of the one of A or B, right? Because A or B is true, 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 false. So this one's pretty convenient. I can just take the not of A or B. So A down arrow B is equivalent to not A or B. And if you were asked to prove this, maybe on Thursday, maybe not, the one and only way to do so is with a truth table. Is that clear? Yeah.
Are truth tables effective when writing out mathematical proofs? You can just write out a truth table for this is why.
Yeah, so as you'll see when we start talking about proofs, a proof is something to convince you that in all cases, this statement that you're making is true. And that's literally exactly what a truth table does. In all cases, these two things are the same. So a truth table is a valid proof. And we'll talk more about proofs in a few classes. If you want, I think it's an interesting exercise to try and write the negation of A in terms of this, which is ends up being A down arrow A, and then you want to write A or B, and then you can combine those things and write A implies B. Okay? Just if you're interested, we saw that A down arrow B is not A or B. So if we take the negation of both sides, we get not A or B, which is just A or B. Right? But we found that not is equivalent to A down arrow A. So this tells you that A or B is equivalent to A down arrow B, down arrow, A down arrow B. Okay, and this was very quick. I understand that. But take a look at the solutions because it walks through it a little with a little bit more detail. Okay, feel free to come out to office hours if you have any questions. Remember, please try and be here as soon as possible and enroll in the units for the course. Okay? And I'll see you on Thursday for our quiz.